Good morning to everyone. I'm Antonio Longa, and I'm here to present this journey that me and Gabriele Santin decided to start. The idea is that nowadays geometric deep learning is becoming really useful in many areas, and we make some trouble. We had some trouble finding material and easy to use code. So the idea is to start this journey together. And the idea is that we will have every weekend weekly meeting, and we will discuss about geometric deep learning and present something. Today we are gonna see something really basic and just an introduction. The biggest part of this tutorial will be theoretical, and then we will see something related to the implementation. So let me share my screen. And I prepared some slides. And okay, the title of the presentation of today is "What is Geometric Deep Learning?" And just present this. Okay. As I said, we are Antonio Longa and Gabriele Santin. This is an open source project, meaning that everyone can use our code, have a look on YouTube on our videos. And the idea is to learn how to use geometric deep learning. We will use the framework Pytorch Geometric that has been released a few years ago, so it's quite new. How it works, we will have a brief introduction to a geometric deep learning model, and then we will apply the model we just presented. And the idea is to keep update with the news. And if you, I don't know, if you find an interesting model and you want to present it, just feel free to join us, ask, and present whatever you want. Who are you? The idea is that you can be a student, a researcher, an engineer, whatever you want. And it's obviously totally free, and you can join us and follow everything. Just to say, we have an official website that is geometric deep learning tutorial, Pytorch geometric tutorial. And here we will see for every lecture a new post and with a brief summary. And finally, we will find the video on YouTube, the link to the video to YouTube, and also the repository on GitHub containing the material, the slides, and the Jupyter notebook. Okay, let's start. Okay, where we were here. Okay, today we are gonna see deep learning and which are the fields of deep learning. Then we are gonna talk about graph and graphs representation, and some deep learning and deep learning problems in terms of graphs and deep learning, some definition, graph neural networks, and a little bit of practice. Let's start. As you probably know, deep learning has been in the last decades has been used in several areas like medical images, speech recognition, and in the last decades we achieved amazing results through deep learning techniques on these fields. But what about other fields like biology, recommendation system, network science, or main food? Well, which is the difference, the main difference between an image and a manifold, or a speech and a molecular, an RX image and a graph? Well, the latest stay on non-Euclidean domains. And talking about the graphs, we have several types of graphs, like directed graph, node-labeled graphs, undirected graphs, edge-labeled graphs. So as you can see, this kind of structure has a specific structure, and cannot be modeled as an image that basically is a grid of pixel, or a speech that can be seen as a chain of information. And talking about the graph representation, a graph can be, as you probably know, a graph can be represented with an adiacentesis matrices. What does it mean? It means that if the graph has, I don't know, 6 nodes, like in this example, we have these matrices 6 by 6, 6 times 6, in which the element in position AJ is 0, is 1 if there is an arch in the graph, and it's 0 otherwise. In such a case, we have an undirected graph, so the adiacentesis matrix is symmetric. Okay, but if we have these matrices, these well-structured squared matrices, why we cannot use neural networks? I mean, an image, we say that it's a square is a matrix, and which is the difference between a matrix, an image and an adiacentesis matrices, and why we cannot give as an input our adiacentesis matrix to our neural network? Even convolution, if we think about convolution, well, basically the idea is to make inference on on a little size of the image and make a convolution on that part. We could do the same in a graph. We have these matrices, and we can took small portion of the image and compute something, some convolution. And well, the work is done, we have finished, and the course is finished. Unfortunately, doesn't work, because this is not a good idea. Actually, it's a terrible idea, because what happened if a new edge pop in the graph? So what happened if we have different sizes of graphs? And another big problem is that the matrix representing a graph, this adiacentesis matrix, is not invariant to node ordering. So what does it mean, different size? Simply, as I introduced you, suppose that this new node G appears on the graph, and then also the adiacentesis matrices will be bigger, like in this figure. And if we trained our model to this first neural network, then we will need a new input, exactly, yeah. And the network is not trained to do this. So this is a problem. Another problem is that the adiacentesis matrix is not invariant to node ordering. What does it mean? If we have these two graphs, as you can see, the only difference of these two graphs are the node ordering, I mean, the name that I give to the nodes, but the graphs are isomorphic. In fact, G is equal to G prime. But if we have a look to the adiacenthesis matrices, the adiacenthesis matrices of G and G prime are totally different, even if the graph is identical. And this is why we cannot use the simple geometric, the well-known deep learning on images. We cannot use it for graphs. And as I said, the motivation now is obvious. Not invariant to node ordering, and also its different size create huge problems. Okay, just a really brief definition. We have a graph like this one that is defined as a pair of vertices and edges. And we have the representation of this graph structure and adiacenthesis matrices. And moreover, I mean, we also have a feature matrix, a node feature matrices that is a matrices as you can see, the number of rows is equal to the number of nodes in the graph, while the number of columns is equal to the number of a feature on each node. And we just have this additional information on the graph. So from now to the end, we will use G as a general graph, A as a adiacenthesis matrix of the graph, and X as the node feature, the matrix containing the node features of the graph. Okay, we are going to present the graph neural networks. First of all, we have to define what's so-called computation graph. And then we are going to use the computation graph to infer something from the graph. Okay, what is the computation graph? The computation graph is the neighbor of a node define its computation graph. What does it mean? Just took this example. We want to make some inference on the node A, the red node in the slide. We just took the node A and we add these boxes, and this box, I will tell you what these boxes is later. Then we took the second node, the node connected to A, and then we connect again these boxes, and we connect all the nodes connected to F. What does it mean? We have B, A, and E connected to these boxes that goes inside F, that goes inside this new box and goes to A. What does it mean? It means that we have the feature vector, the node feature of the node A, the feature of the node B, and the feature of the node E. Such information goes inside this box. In some way, they are combined with the feature of the node F, and they goes inside the node A. Yeah, just was I was saying that. Okay, here we have the representation of the node feature of A, B, and E. What those boxes are? Well, they are neural networks. And what is inside this operation? I mean, what we can do with the representation of A, B, and E? We have to do an aggregation. In particular, we have to do an order invariant aggregation. Like, for instance, the sum is order invariant. The average is order invariant. Because it doesn't matter if we add ABE or if we add BAE, the result will be the same. And it's important to have an aggregator that is ordering invariant. Okay, every node defines its own computation graph. So for instance, you already saw this computation graph for the node A, for the node B. As you can see, at the first step, we have 3 different nodes, F, E, and C. And here you can see A, E, F, C. And then the neighborhood again. For instance, from F, we have A and E and B. So we have A, B, and E. From C, we have E and B, and B and E. And so on. The same for C, D, E, and F. And so we have this computation graph for each node in the network, okay? Can you see some redundancy? Yes, of course. For instance, this part in which the node F is involved on the representation of A, we have here the same, here the same, here the same, and it's equal for B, C, every node. As you can see, they are repeated. Okay, in terms of neural network, what we have the layer 0, in which we have the representation of the node feature, the layer 1, in which we have some kind of hidden layer, and then we have our last layer in this little example. Well, a question is how much you have to unroll. Well, suppose that you want to make some inference to that node, the red node in the graph. Well, if I unroll 1 time, I will arrive here. 2 times, I will arrive here. And one question is when I have to stop unrolling this information. Well, in terms of, for instance, social network, probably in order to infer something about me, probably is not necessary to take information also from a guy living in Boston who I never met, and I not even know who he is. But maybe my friends know something about me. The friends of my friends know something about me. It's also important to think about the diameter of a network, because if you unroll too much, then you are seeing for every node, you are collecting information from all the network. And, well, probably is not useful for it. Okay, let's start with a little bit of math. So, okay, we have that the each represent the representation of the node V in the layer 0. Well, the representation of node V at layer 0 is the node V itself. What does it mean? In our previous example, where we had this vector of 3 integers as a node feature, in the layer 0, we have that the representation of the node is just the feature vector. Then what we have some computation in which we have that the node, the representation of node V in the layer k plus 1 is equal to something. And finally, we can see that the representation of node V, we call the embedding of V, Z of V, is equal to the last layer, so the kth layer of the node V. Okay. Now we want to look inside this equation. Is just the copy of this middle, equation. Yeah. Okay, let's start. we already said that this is the k+1 embedding representation of the node V. It's a latent representation. Then we have that this is equal to the embedding of node V at the kth embedding. So what does it mean? My embedding in the next layer is equal to my previous embedding in the previous layer. So we have just h of V at the kth level. Okay. And then we have this operation for each that basically is the average of the previous embedding of the previous representation, the representation in the previous layer of every neighborhood of the node V. Okay. Then what we have? We have two weights, W and B, associated to this layer. And finally, we have an activation function, a non-linearity, for instance, ReLU. And as you can see, here we have a summation. Okay, here we have a mean about all the neighborhood of the node, of the current node. We have some trainable weights. And we have, again, trainable weights and my previous embedding. And we just sum it, pass through an activation function, and we have the representation of the k+1 layer. As you can imagine, all these structures share the parameters wk and bk. And it's the same for each element in the network. I mean, not for each element, sorry, for each computation graph we have, these parameters are shared together because it allows to, when a new node arrived or a node that we didn't use for training, but we want to use for testing, we are able to build what we called previously unroll and build a computation graph. Then we have the already trained weights W and K for each layer, W and B for each layer, and we can propagate the information and produce the embedding of node E. Okay, we are close to go to the practice side. I want just to talk about GraphSAGE because it's really an easy modification of what we did so far. And moreover, it allows us to give representation, already build function on Pytorch, so we can see in practice what does it mean. Okay, GraphSAGE is a work done by William Hamilton in 2018, and these three equations are the same we saw previously. Okay, which is the difference with respect to this new paper? Well, they change only this middle equation, the equation for the middle, the hidden layers. And what they do? Well, instead of using the average here, they use a general aggregation. Okay, and it's the same. Here we have aggregation. Here we have a mean. And as you can see, for every neighborhood, every node in the neighborhood of the node V, and above it's the same for every node in the neighborhood of the node V. Instead of doing the mean, we do something else that we will see. And another modification that they do, actually they did, was to, instead of summing the information given by myself in the previous layer, so bk and multiplied by vk, instead to sum together this information. So as I said, the information came from my neighborhood and the information came from myself. Instead of do this, Hamilton decided to concatenate this information. Okay, so as you can see here is just a concatenation. In fact, as you can see here, we have the first part that changed, so a general aggregation function, and then we have from a plus, we go to a comma, meaning a concatenation. Okay, what this aggregation is? Well, it can be a pooling strategy, like element-wise, min, max, or whatever you want, or also even LSTM. Note that an LSTM, or we will see everything of this in the next tutorial, not today, but just to say something. Note that LSTM is not orderly invariant. However, there are some works that assert that if you compute LSTM several times with random permutation of the input, you can achieve quite good results. But I don't want to talk about these because this is just an introduction. Okay, I think we have done. I presented the general idea, and now I want to show you a really simple example in a way that you can try this at home. Okay. Okay, let's start. Simply at the beginning, we just import Torch Geometric, and we are going to use already defined data set. So we are not to use our own data set, but we are going to download it from Torch Geometric. And in particular, it's really simple. We give a name of the data set. We call this function, and then we set a root, meaning that it will create a folder with all the file. Suppose that I'm gonna delete this folder and we are gonna run it. What happened? It starts downloading from internet the data set and then build it. As you can see here, Torch Geometric built this folder containing the raw file, so this Cora dataset in a raw file fashion, and also the proceed file. What does it mean? It means that if already I have this dataset, and the next time I'm gonna, I don't know, suppose restart the kernel and clear output, okay, and run again, you can see Pytorch Geometric can see that the file is already in the downloaded, and it just loaded without any download again. Okay. What about the dataset properties? Dataset, in our case, is Cora. That is a citation graph in which is a graph representing different paper and how they are cited among them. So as you can see here, if we print the data set, we can see that its name is Cora. And then if we look at the length of the data set is 1, because we have just one graph, one huge graph. We also have this property, number of classes. We have 7 different classes. We have node feature. So in particular, each node has 1,433 feature. And also we have 0 edge feature. You can see all this information only with exceeding the property of the data set. The data set also have the data we are going to use. In particular, the graph is represented as edge index. So simply have a look here in the first print. The edge index as a size, as a shape of 2 multiplied by this number here. That's the same here. As you can see, here, we have the node 0 goes in the node 633. The node 0 goes, and so on. We also have a training mask, a test mask, and a validation mask. Those are vector, as you can see, I mean, one-dimensional tensor. And we have Boolean values representing which nodes are on the train set, on the test set, and on the validation set. We also have X. X is the node feature. As I said to you, is quite huge. We have 1,433 feature for node. In fact, the shape of the X is the number of nodes multiplied by the number of node feature. And here is just an example. Finally, we have Y. Y is the node labeling. The node labeling. So every node belongs to a different category. For instance, the node 0 belongs to category 3, the node 1 belongs to category 4, and so on and so forth. Okay. Here we took the data, loaded the data without. Actually, in the next lecture, we will see how to load your own graph, your own dataset. We will see functions that allow you to convert from network X to Pytorch, from Pytorch to network X, and several others functions. Okay, here we are importing again torch functional as F. They came from the original library, the torch library. And then we are import SAGE-conf. That is the last slide I show you, from Pytorch Geometric. Here we are gonna say that the data is the dataset in position 0 because we have only one dataset. What we are gonna do here, we are gonna define our neural network. Easily is kind of standard. We define this class, inherited from Torch NN module. We define the init function that is called super itself and call the init function. But don't be scared about this because we will, this is just an easy example to show you how it's easy to run it, but we are not gonna cover the details of this implementation. We will see it in the next lecture. but this is just the beginning, and I want to introduce you to the framework and see and show you how can you use it. So we were here. We just defined this self conv. Oops, conv. We call the convolution layer we just imported, and the convolution layer require an input channel and an output channel. And what we do, actually, we just do a dataset dot number of feature. So meaning that this input is huge, is this number here, and the output is the number of classes, so 7. As you can imagine, this is not going to work very well because we are passing from directly from 1000 and so on to 4 feature. We can specify the aggregation we want to use. And for instance, I decided to use the max. Okay, and this is just the initialization of the network. Then we have the forward. So we just define that the x is equal to the convolution. So the function defined here, and we pass in input the data and the edge index. That is what it requires to run. And finally, we return the log softmax of the function. Don't worry about this and else, but we are gonna talk with everything in details. Don't worry. Here we can use. Okay, what does this function do? Well, this function allows us to decide if to put our model on the CPU or in on the GPU. For instance, in my PC, I have enabled and installed all the libraries for CUDA. So my device is CUDA because it's available. And what happened? We move our model, so our network, and also our data to the GPU. But don't worry, really, we are gonna cover it. We have an optimizer, and whom is already know about machine learning probably already know this optimizer is Adam. Taking input the parameters of the model, it has a learning rate, a weight decay, but we will cover with more time and much more details this stuff. And then we have 2 simple functions, one for the train, in which we train our model, and one for the test. And I'm not gonna spend time here on this simple 2 function because we will cover it, as I said. And then we are gonna just to run it for 100 epochs and see the results. Okay, here we have the validation on in the test in accuracy. Yes, the validation and the test accuracy with this toy example. As you can see, there is no improvement, quite stable. We did few epochs, but who cares? Because really the model is really simple. We don't have dropout, we don't have linear layers, we don't have almost anything. And that's all. I really wanted just to show you the basics and introduce you to me and present this idea to, I don't know, work together and learn together Pytorch Geometric. Does anyone has any question?
I have a question actually. So first of all, thank you. Very great introduction. So I'm almost new to this library PyTorch, and I also got a small connection problem at the very beginning. So I don't know if you already covered it. So I was curious about the let's say problems in the sense of classification, regression, and so on that you can tackle actually with this. Uh, Geometric neural networks in the sense that you presented like a classification of nodes, right? So is there anything else that you can do?
Yeah, of course, because let me share my screen. Okay, here, here, when we have this, okay, this one is really, really sample. But when we have this, we can also, instead of using softmax, we can use, actually what we have is a node embedding representation. We have a learned representation for each node. And then we can use such representation for everything, regression, whatever you want, because what you have learned so far is a node representation.
Okay, great. So you can also do stuff with the edges, like classify edges. Okay, great.
Well, actually, well, we are gonna cover this definitely because I think it's interesting. But basically, what you do if you have, if you want to do something related to edges, well, instead of build this computation graph, you build it is in terms of couples. For instance, the edge between A and F appears here. And the neighborhood edges, instead of having nodes, you have representation of edges.
Okay.
Okay.
Yeah, thank you.
Okay, someone else?
I have one curiosity.
Mm-hmm.
You showed us that interesting framework in which from each node you basically collect information from its neighborhood, its neighbors, and then you might unroll the network as much as you want.
Exactly.
My question concern the case in which you have, for example, self loops. What does happens if you have self loops? So you're basically feeding your hidden layer with the let's say information from the node. Then you're basically let's say it's the level 0 of what should happen when you unroll too much. That you're, I don't know, it's a kind of overfitting or what is it?
Well, I think you can handle in different ways. For instance, if you think about the math we just saw, we still have the representation of ourself, but you can even think to remove self loop or limitate them after a while. You see what I mean? I mean, instead of keep cycling on itself, you can do this up to a given time and then stop it.
Yeah, so basically you're treating self loops, let's say self edges, as a different type of connection from there.
Yeah, but I'm sure that someone has already tackled this problem. But so right now I've read nothing about it. But interesting. Thanks.
No, it was just a curiosity. I mean, I don't even know if it's really overfitting or what is it doing. So it was just. But thanks.
I don't think so, but anyway.
I
Okay.
think we can maybe keep these in mind for a future
Yeah.
meeting. So just discuss what happens in those cases and
Yeah. Be a great idea. Yes.
So something that I didn't, so I'm really new also to this topic, so that the number of layers is related to the size of the neighborhood that you are considering, right? So because every time that you compute a new layer, you are increasing the computational graph, right?
Yeah. But exactly. Maybe I didn't explain it very well.
No, it was really clear, I think so.
But you're right. We have two levels of depth, in a sense that, for instance, here we have really two levels of depth, because so far we can see that it seems that this computation graph is a depth of 3, because first, second, and third. Well, 2, but by the way. But note that we have the depth of the computation graph, and then we have the depth of the network. This neural network can be depth as much as I want. I mean,
okay, I see. So those are You can...
in these terms, we have different depth. Different depth.
Okay, I see. Yeah, because I think it's much more expensive if you have. So if you increase, you want a method that is local. So you don't want to consider the entire graph every time. So if you have a very deep structure, you need to consider very large parts of the graph every time. So
Exactly.
yeah,
And
okay,
the basic idea is that often, in order to make inference about one node, probably is not so important to go so wide and deep.
Okay.
Okay. Thank you. And I hope to see you also next week. And I think next week we are going to see with Gabriele some basics of Pytorch. So what we saw today, but in a more specific way and in Pytorch, not in Pytorch Geometric. And then we are going to move to Pytorch Geometric. Thank you, guys.
Thank you.
Thank you.
Thank you.